In this lesson, we'll talk about polynomial functions and operations on polynomials, including composition of polynomials. Any polynomial function of degree n can be written in the form p of x equals an x to the n plus an minus 1 x to the n minus 1, and so on until we'll get a1x plus a0. Those coefficients an until a0 are real numbers, and n is any whole number. That includes the situation when n is 0, which would indicate the 0-degree polynomials. That means just constant ones. Also, we require that an is different than 0. Why? Well, to make sure that we actually deal with the nth-degree polynomial, otherwise this term would disappear. Notice that polynomials can be evaluated for every real number. Why? Because if we have a real number, we can always raise it to certain exponent, multiply by certain number, and then add those real numbers and get the value. So the domain of any polynomial is all real numbers. Let's try to evaluate this particular quadratic trinomial. We will call it f of x for easier reference. We need to evaluate what f of -1 is. That can be calculated by replacing all x values in the f of x formula by -1. So we go -2, and then let's leave a bracket for this value, square, and then it's minus, again, value for x, put a bracket, plus 5. The incoming x value is -1, so we place -1 instead of all previous x's. And now what's left to do is just to evaluate this expression. We have -2 times -1 square. Recall the order of operations. We need to square the -1 first. That becomes +1 times -2. That becomes -2 altogether. And then 2 negatives makes it positive, so it's +1 and +5. Therefore, the final answer is 4. Okay, let's do question B. F of 2. The same idea. Maybe this time you pause the video and try to evaluate first on your own. It will be -2. Instead of x, we have 2 square minus, and again, instead of x, we'll have 2 plus 5. Okay, now this square refers to this 2 only, so we'll get 4 from here, times -2, so it's -8, minus 2 and plus 5, so that's the same as plus 3 altogether, equals -5 as a final answer. Did you get the same? Next, let's evaluate f of 1/2. So the same idea, however, this time we'll play with fractions a bit here. Again, I will encourage you to try it on your own first. -2, in the bracket we have 1/2, square it, and then minus, put a bracket, that's 1/2, and plus 5, equals. So we have -2, and then it's times 1/2 square, it's 1/4. So that's the same as -2 over 4 when we multiply. Minus 1/2 and plus 5. Notice the -2/4 is the same as -1/2. So this -1/2 and that -1/2 gives me -1 altogether. Therefore, 5 minus 1 is 4 as a final answer. Okay, let's see the next question. 2 times f of x. Don't be confused by the 2. The 2 is outside of f of x. So we have to write what f of x is and then multiply it by 2. Okay, 2 instead of f of x, let's open a bracket and write down what f of x is. -2x squared minus x plus 5. Whole thing. And then multiply through, we'll get new function. It will be -4x squared, distributive property, -2x, and plus 10. Let's see the next example. This time it's f of x minus 5. So f of x by itself is this whole expression. Okay, let's write it down. -2x squared minus x plus 5. And then we are subtracting 5 from outside of this function. Our whole function is here, and then we're subtracting 5. Here we can notice that this -5 can be reduced with the plus 5. So the overall expression becomes -2x squared minus x as a final answer. Let's try f of a. Well, f of a is really easy. We just need to replace x by a. So everything is the same except that instead of x we write a. In the last question we need to evaluate f of something bigger, of a plus 1, of the whole expression. But let's do it nice and slowly, and every time we encounter an x, let's place a bracket. -2 bracket, that will be our future input. Let's make a little bit more room because a plus 1 is coming. Square minus x, but x is a bracket, and then plus 5. The bracket contains a plus 1. That's our input, a plus 1. So what's left to do is simplify this expression. So let's copy the -2, then square this binomial. Remember the formula, perfect square of two terms is the first term square plus double the product of the two terms, so it's 2a, and then plus last term square. Complete the bracket. Now we open that second bracket, it will become -a, -1, and copy the 5. Okay, one more step. We need to distribute the -2 to the bracket. So we have -2a squared, -4a, and -2. Then copy -a. We can combine these two free numbers. 5 minus 1 is plus 4. And again, one more time, combine like terms. So we have -2a squared, -4a, and -1a is -5a, and 4 minus 2 is plus 2. That will be our final answer for this question. The set of polynomials is closed under addition, subtraction, multiplication, and composition. What does it mean? Well, that means that if we take two polynomials and perform one of those operations, including composition, then the result is also a polynomial. Since polynomials are special types of functions, and when we add or subtract those functions, we obtain a polynomial which is the same type of function. Maybe we could define a function that is either sum or difference of two previously chosen functions. So if we work with a function f with the domain d sub f and a function g with the domain d sub g, we can define a new function that will be the sum of the two functions in the following manner. This new function, denoted f plus g, will be defined on any x as a sum of values of the function f and the function g at the same point x. Similarly, the difference of two functions can be defined by coordinates. That means the value of the new function, denoted by f minus g, at certain point x is defined as the difference of values of the function f and the function g at the same point x. At first it may look like a bit confusing, but just remember that whatever is before the x, that's just a name of a function. So f plus g, it's a name of a new function. We could easily call it h. However, we use f plus g in order to indicate which function we have in mind. Similarly with subtraction, this notation f minus g, that's just a name of a new function, and this is the definition of this function. We know how to calculate the value of this function f minus g at every single point x, just by taking the value of f and subtracting the value of g at the same point x. Okay, since we defined two new functions, the sum and the difference, how can we figure out the domain of those functions? Well, the domain of the sum or difference function is just the intersection of the two domains, of the domain of f and the domain of g. This comes directly from the definition of the sum and difference. In order to create the value of the new function, we have to use values of the f function and g function at the same point. So this particular x must belong to the domain of f and also must belong to the domain of g. Therefore, the domain of f plus g or f minus g must be the intersection of the two domains. So that's theory. Now let's practice. What does it mean for particular polynomials? P of x is defined as 2x minus 1 and s of x is defined as x squared plus 2x minus 1. Let's find the following. In order to find those expressions, we need to fully understand how this notation works. P plus s, this whole business here, is just the name of a new function, and we evaluate this function at the input tray. So according to definition, the sum of the function p and s at the point tray is the same as the sum of two values, p at the point tray and s at the point tray. So that's directly from the definition of the sum of two functions. And then we can refer to the p function and evaluate p at the point tray. So instead of x, we'll have tray. Therefore, we get 2 times tray minus 1. That's our p of tray. And then we're adding s of tray. So follow that recipe. We go tray squared plus 2 times tray and minus 1. This is our s of tray function. Okay, to finish it, we just need to use some arithmetic. So 6 minus 1 is 5, plus 3 squared is 9, plus 6 minus 1, so plus another 5. Altogether 19. Therefore, the value of this function p plus s at the point 3 is equal to 19. Now let's do the same, but generally for the function p plus s of x. So that just means that we need to take p of x plus s of x directly from definition. But p of x is this much. So we replace what p of x is, 2x minus 1, and then plus s of x, which is that much. So we write x squared plus 2x minus 1. And finally we simplify this polynomial to x squared, and then 2x plus 2x is plus 4x, and minus 1 is minus 2. So now we see what is this new function. That's another quadratic polynomial that is obviously not the same as s and not the same as p. It's just totally new polynomial. Okay, let's do the same with the difference of functions. According to the definition, we're supposed to take s of x and subtract p of x. And now let's plug in what s of x is. That's this trinomial, x squared plus 2x minus 1, and then we are subtracting, but since we're subtracting, remember we need to put a bracket before the incoming expression. So the p of x is 2x minus 1. Close the bracket and simplify. So just to take care of this minus, let's rewrite everything with no bracket. So it will be x squared plus 2x minus 1 minus 2x and plus 1 equals, and let's collect like terms. We can notice that 2x will cancel the negative 2x and negative 1 will cancel 1. So altogether this difference of two polynomials is actually x squared, a simpler polynomial this time. Okay, now since we already know what is this function s minus p of x, it's here, then we can take advantage of it and evaluate s minus p at the point negative 1. So just plug in negative 1 instead of x, negative 1 squared, which equals just 1. Notice that if we wouldn't have this function calculated, we would just go the same way as with the sum of functions. We would evaluate s of negative 1 and then minus p of negative 1. But in this case, we could take advantage of what we've done already. And finally, let's look at p minus s of a. Well, it's not the same as s minus p, because the order is different. We have to start with p. So according to definition, that's p of a minus s of a. And p of a, according to the formula, is 2 times a minus 1, and then minus, red alert, anytime we have a minus, let's place a bracket around the incoming expression. And here we write s of a. So we follow that formula, a squared plus 2a minus 1. And now we need to release the bracket and simplify. So let's copy everything with no bracket anymore. So it will be negative a squared, negative 2a, and plus 1. And now what's left to do is to simplify like terms. Again, we can notice that 2a cancels negative 2a and negative 1 cancels 1. So we end up with negative a squared. Very similar to this example. Instead of x we have a, but with opposite sign. Why opposite sign? Well, I'm sure you know it already, because we calculated p minus s rather than s minus p. So, opposite function. Okay, we talk about addition and subtraction. Now let's talk about composition of two functions. The composition of a function f and g is defined as follows. First of all, we denote the composition by using a little circle, open circle at the middle of the line, which is not the same as multiplication. It's a composition. And this new function, that's a name of the new function, is defined at every point x as g of f of x. So what's happened, we calculate what f of x is first, and then plug in this value inside the g function. So it's like chain. The value of the inner function becomes the input for the outer function g. Obviously, this can be performed only when the value f of x is really in the domain of g, because otherwise we wouldn't be able to evaluate g at this point. Generally, the domain of the composition of two functions is not so obvious. However, since we are talking about very special functions, very nice ones, polynomial functions, for polynomial functions we don't have any trouble, and the domain of any composition of two polynomials is all real numbers. Here's a diagram that should help us to understand the composition of two functions. Imagine we have three islands, the blue one, the pink one, and the green one. Let this blue island be called x, and let this x serve as a domain for the function f. The function f could be a ferry that, for example, takes people from the blue island and carry them to the pink island. An input x from the blue island, when carried by the function f, lands on the pink island y, and it's called f of x. That's the value of the function. However, if this f of x wants to travel to the green island, it will have to take another ferry. That will be the red ferry, called g function. It brings this input f of x to the green island to land as an output g of f of x. Now imagine that the input x wants to travel to the green island z directly, just by one ferry. This can be done using the green ferry h. This green ferry is the composition of the two functions f and g. Therefore, the input x lands on the green island as a value of the composition function g composed f at the point x. So, since the result of traveling by ferries f and g should be the same as of traveling by the ferry h, then from here we know that g composed f at the point x really means the same as applying f to x and then applying g to the result f of x. Notice that the input x first travels by the function f and then by the function g. That means in this notation, g composed f, the f operates on x first, and then when we finish this operation, then we apply g. So whichever function is closer to x, that's the function that operates first on x. We'll see how this works on specific examples on the next slide. Now, the intuitive part of the composition is like moving certain items from one person to the other person to the next person, because we can compose a lot of functions. So you can think of one function from here to there, then from here to there, then from here to there, and so on. Okay, here's our time to practice. Let our function f of x be 3x minus 2, which is a linear function, linear polynomial, and g of x be x squared plus 1, a quadratic polynomial. Find the following. And now we really need to understand the notation. If you see this little circle at the middle, that means composition. This is not multiplication. Okay, so we compose g with f at the point 2, where f operates on 2 first. So let's rewrite g for later, and now take care of f of 2. F of 2. Okay, so we copy g patiently. First, we need to figure out what f of 2 is. Well, refer to the f function and replace x by 2. So that's 3 times 2 minus 2. Okay, let's calculate how much is that. G of 6 minus 2 of 4. Oh, that's great, because now we know perfectly well how to find out g of 4. We refer to the g function and plug in 4 instead of x. So it's 4 squared plus 1. And this equals to 17. Great. Now the second question, which is very similar to the first, but the order of f and g is different. I would suggest that you stop the video and try to evaluate this expression following the first example. That would be f of g of 2. So we copy the f, and then we figure out what g of 2 is. So let's refer to the g function. It asks us to take the input, square it, and add 1. So input 2, square it, and add 1. Okay, now let's calculate how much is that. F of 5. And the last step would be to use the f function, refer to the f recipe, 3 times the input minus 2, and evaluate. 3 times the input, which is 5, minus 2. So altogether we have 15 minus 2, it's 13. Did you get the same answer? Okay, so in the last two examples, we evaluated the composition of the two functions at specific point. The answer was one single value. This time, we try to find out the overall function. What is this new function for any x? So it's not a specific value that we'll expect, but the expression, another polynomial. Okay, let's follow the definition. G of f of x. F operates on x first. So, keep the g for later. Figure out what f of x is. F of x refers to this expression, so it's 3 times the input, which is x, minus 2. And now this whole expression becomes input to the g function. But the g function tells us to take the input, let's put a bracket for now, square it, and add 1. The input is 3x minus 2. This whole expression, that's our input, so we need to write it here. Okay, let's do it. 3x minus 2. And finally, let's evaluate this expression. So we need to perform perfect square. Hopefully you can recall perfect square formula. Maybe I will write it on the side so you remember it. A minus b. When we square it, it becomes a squared minus double the product of a and b, and plus b squared. We're going to refer to this. So the first term square, we're squaring just this 3x, it becomes 9x squared. Then we have a minus 2 times ab, 2 times this term and that term. So 2 times 2 is 4, times 3 is 12x, plus last term square, which is 4. And then the last number plus 1. So the only thing that we still need to do is to add this 4 plus 1. Okay, therefore our answer is 9x squared minus 12x plus 5. That's a new polynomial composition of g and f, where f operates first and g after it. Again, try to do this example by yourself and then come back to the video to see if the answer is the same. So, we have f of g of x. G operates first on the x and then f. So keep the f till we figure out what g of x is. G of x is this much. Okay, so it's x squared plus 1. Okay, and then f tells us to take 3 times the input. Let's use a big bracket for the input. Minus 2. Now, what's the input? The input is x squared plus 1. So we place it here. X squared plus 1. Okay, and simplify. So let's multiply through the bracket. 3x squared plus 3 minus 2. Therefore, overall, our function is 3x squared plus 1. Couple more examples. What's f of 0 is? Well, that's the same as f of 0. Okay, so keep the outside f waiting till we figure out what f of 0 is. F of 0 means we need to plug in 0 into the f formula. So it's 3 times 0 minus 2. Okay, so it's f of 3 times 0, 0 minus 2, so it's negative 2. And now we need to evaluate the same function, but at different point, at negative 2. So we have 3 times negative 2 as the input, minus 2. Okay, so we have negative 6 and negative 2 altogether negative 8. So that's the value. And in the next example, we refer to the same composition of f and f, but generally at any x. So we expect the final answer to be a polynomial, not just a single value, but entire polynomial. F of x. The same function nested inside itself twice. So f of x is 3x minus 2. And then we apply this f to this input, which means we take 3 times the input minus 2. But the input is also 3x minus 2. That's how it looks like. And then we open the bracket and simplify as much as possible. So we have 9x minus 6 minus 2, which really means 9x minus 8. That's our overall composition of f with f function. Finally, g composed with g at the point negative 1. So, do we expect a single value in the end or an expression? Yes, it's a single value because we evaluate it at specific x. So, how much would it be? g of negative 1. We'll leave the outside g waiting for its turn, and we evaluate what the inside g becomes. G of negative 1. Plug in negative 1 to the g formula, it becomes negative 1 squared plus 1. Okay, so this is like 1 plus 1, so it's really 2. And then we evaluate g of 2. G of 2 is 2 squared plus 1, so it's altogether 5. Final answer. I hope you've got the idea, but that obviously requires a lot of practice, so please take some examples from the textbook and practice. The last example is an application problem. Let's see it. An oil well is leaking, with the leak spreading oil over the surface as a circle, like on this picture. At any time t in minutes after the beginning of the leak, the radius of the circular oil slick on the surface is r of t equals 4t feet. So we are given a function, radius in terms of time. Let a of r equals pi r squared represent the area of a circle of radius r. So we have another function, area in respect to radius. And this is the well-known formula, pi r squared. Find and interpret a composed with r of t. So r operates on t first, and then a operates on whatever r of t is. Okay, how can we find this? Well, let's write it down. A composed with r as a new function of t, according to the definition, is the same as a of r of t. Okay, great. Do we know r of t? Yes, we do. R of t is 4t. So that's the same as a of, and the input for the a function is called 4t. Now we can follow the a function. Area of certain input is equal pi times the input square. Let's do it. Pi times the input, put a bracket for the input, square. Our input is 4t, so that's what we place here, 4t. Okay, and then we can simplify. How much is that? Well, inside the bracket we have 16t squared and we have pi. Since customary we write numbers first, so we write 16, then pi is also a number, so we write 16 pi, and then t squared. So that's our formula. Notice that this formula depends only on t. So it's not the radius that is important, the time is important in the end. So how to interpret this A compose R function? Well, this is really the same as area of the circular oil slick with respect to time. So in layman language, this A of R function is actually telling us how much area of the water will be covered by oil after t minutes. So it's actually very useful because we don't need to go and measure the radius. It will be very difficult to do that. However, having this formula, it's enough to plug in the number of minutes, and then we know instantly how much area of water will be damaged by oil.